Hello, in this video we're going to look at derivative rules, which are section 3.1 and 3.2 in your textbook. Now the motivation for this section would be the following question. What is the derivative of x to the power 10? Now if you think about it at first, you might say, well, I can just follow my three steps. Step 1 would be to calculate f of x plus h. Well, that would be x plus h to the power of 10, which means you have to FOIL this out 10 times. I mean, that's pretty horrible. That's a lot of work to expand this 10 times. No one wants to expand this. No one wants to expand this because it's going to take so long. And what if instead of it being x to the power of 10, it was x to the power of 100? I mean, it just becomes ridiculous. There must be some rule, some way, some technique of doing these without having to expand them every single time. And indeed, there is. We're going to look at some rules as we go through it. And one thing I want to explain to you is that you could expand this out 10 times and you would get the same answer. It would be correct. But a lot of mathematics is actually about becoming efficient. Let me give you an example. Back in the day, you might have learned to add like this. 3 plus 3 plus 3 plus 3 plus 3. And you could do 3 plus 3 is 6, plus 3 is 9, plus another 3 is 12, plus another 3 is 15. But eventually, at some point in your mathematical journey, you learned that you could just do 3 times 5. Because, well, 3 times 5 will be the same thing as 3 plus 3 plus 3 plus 3 plus 3. You've got 5 groups of 3. Okay. Well, what if you had the same idea here? 3 times 3 times 3 times 3 times 3. Well, again, you could do 3 times 3, which will be 9, and then times another 3 is 27, times another 3 is 81, times another 3 will be 243. But again, hopefully in your mathematical journey, at some point, someone explained to you that you could just do 3 to the power of 5, because you have 5 copies of 3 that are all being multiplied. And so in that sense, 3 to the power of 5, or 3 times 5, both of these are more efficient ways of writing and calculating these expressions. Math is about making things more compact, more efficient, quicker. You want to be optimal when you're doing math. And so in the same light, we're going to look at these derivative rules to try to speed up our process of calculating derivatives. It's not that the definition and the 3 steps are wrong, it's just that they're not as fast as they could be. So let's go ahead and look at our first rule. So rule number 1, let's let fx be c, where c is a constant. Then the derivative is 0. Well, let's do an example here. Let's say our function was fx equal to 4. Apparently, the derivative then would just be 0. Well, let's look at the proof. We actually don't need to do all 3 steps because it's pretty straightforward. It's an easy function, so we'll jump right to the limit. So limit h approaches 0 of f of x plus h minus fx over h. Well, the thing is that f of x plus h means everywhere you see x, replace it with x plus h. But f of x is just c, so there is no x here to replace with x plus h. So f of x plus h is just c, and f of x is still c over h. Now c minus c will be 0, and 0 divided by anything, of course, is always 0. So we have the limit of 0. And the limit of a constant, of course, is just the constant. So there you go. We have the derivative equal to just 0. So we can put a little box there, and we proved our first rule. Now we're going to look at our second rule, but before we do, I just want us to recall a few facts that we've proved so far. Now on the very first day of class, we proved that if fx was equal to x squared, the slope of the tangent line had the following formula, 2x. So the derivative was 2x. And somewhere along the way, when we had f of x equal to x cubed, we found that the derivative was equal to 3x squared. Now, hopefully you see a bit of a pattern here. The 2 here makes a 2 there, and the 3 here makes a 3 there. But what's happening is that the power of x here is only decreasing by 1. It's going from 3 to 2, or it's going from 2, and maybe it's a little tricky here because it's not written, but there's an invisible 1 there on the x. So if you were to take a guess at the derivative when f of x is equal to x to the 10, hopefully your guess would be 10x to the 9. What we do is we take that power and we bring it on down, and then we subtract 1 from the power. And that is indeed the correct answer. So we're going to go ahead and prove that, but hopefully you see the motivation from the examples that we've looked at thus far. All right, so back to our rule number 2 here. F of x is equal to x to the n, where n is a natural number. And we know that the derivative, we're going to prove it in a minute, the derivative is nx to the n minus 1. So in an example, if f of x is x to the 10, then the derivative is simply 10x to the 9. You bring down the power and you subtract 1 from the power. All right, let's go ahead and do the proof. So step 1, we calculate f of x plus h. In this case, it'll be x plus h to the power n. Now again, no one wants to expand this, but we have to do it one time, at least once in our proof. It's kind of like we expand it one time, and then that counts for all times, because we do it once, we get our result, and we never have to use it again, the expansion that is. So to expand this, we're going to need the binomial theorem. Some students incorrectly expand this as just x to the n plus h to the n, right? That is not correct. You can't do that. I'm just going to even erase that right away because I don't want you to see that. You can't just take the n and distribute it to both across the addition. That only works if this is multiplication. When it's addition, you have to use the binomial theorem. So you get, if you remember, nc0 x to the n plus nc1 x to the n minus 1h plus nc2 x to the n minus 2 h to the 2 and so on. And this just continues on and on and on and on and on until you get to the very end where you have ncn and h to the n. Again, the rule is you write these coefficients, nc0, nc1, nc2, as the coefficients. They come from Pascal's triangle. Then the powers of x go down, so they're x to the n minus 1, x to the n minus 2. And in concert, the powers of h go up. So there's an h to the 0 missing here, h to the 1, h to the 2, all the way to h to the n. All right, so now we can calculate step 2, f of x plus h minus f of x. Well, f of x plus h is the same thing, so nc0, x to the n, nc1, x to the n minus 1h, nc2, x to the n minus 2h squared, plus dot dot dot, ncn h to the n, minus, well, f of x is x to the n. And hopefully you see that that cancels because this first term here, nc0 is equal to just 1. If you remember from Pascal's triangle, or if you were to calculate this using the formula, nc0, if you have n things and you choose 0 of them, there's only one way to do that. So this is 1x to the n. And at the end, we also have 1x to the n. So those are going to cancel out. And now I'm going to go ahead and actually factor on this step because if you notice, there's an h squared, there's an h to the n, there's an h in common with each one of these terms. And so I'm going to go ahead and factor out that h now just to save me some time later on. So we're going to factor out the h, and we're going to get nc1 x to the n minus 1 plus nc2 x to the n minus 2h plus ncn h to the n minus 1. All right, time for step 3. So step 3 is you do the limit as h approaches 0 of f of x plus h minus f of x all over h, which means we do the limit of, well, our whole top thing, which is a big mess, all over just an h. So we rewrite the numerator all over h. And you can see why I factored out the h. I wanted it to cancel. So that's going to give the limit h approaches 0, nc1 x to the n minus 1, nc2 x to the n minus 2, h plus dot dot dot, ncn h to the n minus 1. Now that we canceled the h, we can go ahead and evaluate the limit. And if you notice, this first term has no h, so it's just going to come out as a constant. This term has an h, this term has an h, all the terms in the middle are going to have at least one power of h, so they're all going to go to 0. So we're going to just get nc1 x to the n minus 1 plus 0 plus dot 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 plus a bunch of zeros, which is just nc1 x to the n minus 1. And we might need to do this on the side. If you have n things and you choose one of them, well, there is exactly n ways of doing that. And if you don't remember the formula, or you don't remember the argument for it, remember it's going to be n factorial over n minus 1 factorial 1 factorial. So you have n factorial, which you could write on the top as n times n minus 1 factorial over n minus 1 factorial. The 1 factorial doesn't matter because it's just 1. Those cancel out, and you're left with n. Which means our final answer here is n x to the n minus 1, and that is the derivative, and that is our proof for the rule. So again, it's not fun to expand it. You have to use the binomial theorem. It's a fair bit of work. But once you have expanded it, you can then go ahead and use this rule on all sorts of powers of x. Now, although we will not prove it, this result is actually true for all real n. So it's true when x to the n is maybe x to the 10, but it's also true when you have something like this, because the square root of x could be rewritten as a power. This could be written as x to the 1/2. So to calculate f prime, we use the same rule. We bring down the power, and we subtract 1 from the power. Well, 1/2 subtract 1, we've got to do a little fraction work on the side. That'll be minus 2 over 2, which will be minus 1/2. Let's do the next one. F of x is equal to 1 over x. Again, we need to use a little bit of knowledge here. This could be written as x to the power of negative 1. So that'll be negative 1, x to the negative 2. Now, you can go ahead and simplify these if you want. For example, this one would be negative 1 over x squared. If you were to convert it to a nice power that doesn't have a negative exponent. And this one over here, you could convert to 1 over 2 root x, because you take that 1/2 and make it positive when you put it in the denominator, and then the 1/2, of course, means square root. But you don't always have to simplify derivatives, and we'll look at some examples where sometimes you do have to, and sometimes you don't have to. Now let's do a decimal one here. We have f of x is equal to x to the negative 4.2. So to find the derivative, we simply bring down that power of 4.2, and we get negative 5.2. There you go. Now there's another rule you can use in conjunction with this first rule. It's rule number 3. And it says that if you have a differentiable function, and c is a constant, then the derivative of c f of x is equal to c derivative of f of x. Now I know this notation looks a little bit scary, but all this symbol here, d dx, means is derivative. This just means the derivative. And in this case, what we have is the derivative sort of acting on a function. It's saying that the derivative is going to act on the function c f of x, and instead we can take the constant out. This rule is not really a rule about a specific function that you're going to do the derivative of, like x to the 5, but it's a rule about how the derivative operates. And so it says that when you're doing constants, the derivative says, just take the constant out front. So let's go ahead and look at an example. Suppose you had the derivative of 4x squared. Well, we technically haven't done that yet because we've only done x squared. But it's okay because we could say that 4 is a constant. It goes out front. And we do the derivative of x to the 2, which we know as 2x. And then we just multiply back in that 4 to give us 8. So we get 8x. Now, eventually, when you get comfortable with this rule, you might just bring down that 2 and hit the 4 right away in multiplication. 2 times 4 is 8x, and you'd have your answer in one step. But this is why that works. You're allowed to take that constant out before you do the derivative. So let's go ahead and look at the proof. Again, the proof for this is going to be a little tricky because we don't, again, do our 1, 2, 3 steps because we are just looking at a general function. So there is no f of x plus h to expand. But if we look at the definition, we would have the derivative of c f of x is equal to the limit as h approaches 0 of c fx plus h minus c fx over h. So next up, we're going to notice that there's a c in common with both terms in the numerator. And so we'll factor that out. C fx plus h minus fx over h. Now we need to remember something important about limits. If you have a constant inside of a limit, well, that constant can be factored out. So we can put this as c, the limit h approaches 0 of f of x plus h minus fx over h. And again, the reason why we can do this here is because by limit law, constants factor out of limits, which will then give us, well, limit h approaches 0 of f of x plus h minus f of x over h, that's technically just the derivative of fx. We're just back to the definition of the regular derivative. And so if you notice, we started with the derivative of c f of x, and we ended up with c derivative of f of x, which was our goal, and so we finished our proof. Now again, this is important because why this works, why this rule comes about, is because the derivative is a limit. In fact, the derivative is a special limit. The derivative here is made up of doing f of x plus h minus f of x over h with a limit in front. And so the rules about limits, where constants factor out, translate very nicely to rules about derivatives, because derivatives are based on limits. So let's go ahead and try a derivative question here. F of x is equal to x to the power of pi. Determine the derivative. Go ahead and pause the video and give it a try. All right, so pi here is just a constant. If you remember, it's approximately 3.14. And so the rule says that you take that power, the power of pi, you move it down to the front, and then you subtract 1 from the power. Well, subtracting 1 from pi is just going to be pi minus 1 because we can't actually calculate it. So the answer would be A. Now let's try a more conceptual question here. Let's match the graph with its derivative. So here we have the graph. And which one of these is the derivative? A, B, C, or D? Go ahead and pause the video and think about it for a bit. All right, so hopefully you've given it a try. Now let's look at this graph. What degree does this polynomial look like? Well, hopefully you see the classic wiggle shape here of a degree 3. This is likely some kind of x cubed graph, which means that when you do the derivative of this should be 3x squared. We should be expecting a parabola. So clearly A and C are wrong because they're cubics. the correct answer must be either B or D. Well, how do we know if it's B or D? In this case here, because the cubic is going from the top left to the bottom right, clearly the cubic has some kind of negative in front of it, which means that that negative, which is a constant, will factor out and make the following also negative. So the correct answer is likely B, but let's see if we can add one more piece of evidence. If you notice here, if I was to just draw a tangent line right here, well, it looks like that tangent line would have positive slope. So we would expect the derivative to give us a positive value. And if you notice, if this is our x value, over here for this graph, it's telling us the derivative is below the x-axis, which means it has a negative slope. So D cannot be correct, which means the correct answer must be B. Now just to notice a few other really interesting connections here. The graph has a horizontal tangent right here and a horizontal tangent here. Both of those mean the derivative must be equal to 0 and the derivative must be equal to 0. Interestingly enough, over on the graph of the derivative, at those 2 points we have the graph going through the x-axis, because again the derivative there is equal to 0. Very interesting ideas which we'll explore in future videos. Now for rule 4, we have that the derivative of a sum is the sum of the derivatives. Hopefully that makes some intuitive sense thinking about limits. Remember, the limit of a sum is the sum of the limits. And let's look at an example. Suppose we have the derivative of 3x cubed plus 5x squared. So we're adding two derivatives. Well, the rule says that we could do just the derivative of 3x cubed plus just the derivative of 5x squared. Now, of course, we could go further. We could go ahead and factor out those constants. The derivative of x cubed with the 3 in front, and then the derivative of x squared with the 5 in front. We use our power rule to get 3x squared. We use our power rule here to get 2x. And that's going to give us 9x squared plus 10x. Of course, once you get comfortable with these rules, you can jump from here to here in one step. You don't have to justify all the way along, but that's how it works. That's how you can do derivatives of polynomials, for example. So let's take a look at the proof here. So we're going to start with the derivative of fx plus gx, which means we would have the limit as h approaches 0 of f of x plus h plus g of x plus h minus fx minus gx all over h. Now to do this limit, well, at least to rearrange it, I'm going to put the fx with the fx plus h and the gx with the gx plus h. I'm going to put them side by side. So we would have the limit h approaches 0, fx plus h minus fx plus gx plus h minus gx. This is going to be all over h. Now, one of the rules about fractions is that if you have this and this all over h, you could split it up as just this over h plus this over h. Again, it's kind of the common denominator rule in reverse. You might remember that if you have 3 over 7 plus 5 over 7, you can write that as 3 plus 5 over 7. The rule works in reverse. If you have 3 plus 5 over 7, you could write it as 3 over 7 plus 5 over 7. So that's what we're going to do right here. We're going to write this as the limit. H approaches 0. F of x plus h minus fx over h plus gx plus h minus gx over h. We're going to split it up into two fractions. Well, I'm also going to want to split them up into two limits. And I'm allowed to do that because I have the limit of a sum, which we know is going to be equal to the sum of the limits. So we'll write that down. Limit h approaches 0, fx plus h minus fx over h plus the limit h approaches 0, gx plus h minus gx over h. And of course, the reason we're allowed to do this is by the limit law, that the limit of a sum is the sum of the limits. Limit of a sum is the sum of the limits. Okay, well, we can now recognize that this is simply the definition of the derivative of fx, and this is just the derivative of gx. Well, and there we go. We started with the derivative of the two functions added together, and now we have the derivative of each function on its own added together. And so we've completed our proof. So for homework, you can go ahead and prove that the derivative of f of x minus gx is equal to the derivative of f of x minus the derivative of g of x. It's the same as the proof we just did, but instead of plus, it's going to be minus. And you use the limit law that the limit of a difference is the difference of the limits. So using these laws, let's go ahead and try a couple examples. We have fx equal to 5x to the 10 minus 3 over x plus 7 plus the square root of x cubed. So, of course, we could rewrite this here as negative 3x to the negative 1. And we could rewrite this as x to the 3 over 2. It's a good idea to have your powers of x written explicitly as powers of x, so you can use the power rule. The derivative will be 5 times 10, which is 50, x to the 9. Negative 1 times negative 3 is positive 3, x to the negative 2. The derivative of 7 is just, well, 0, so you can put plus 0 if you want. And the derivative of x to the 3 halves will be 3 halves, x to the 1 half. And there you go. There's your derivative. No need to do the 3 steps, no need to do all those complicated limits and expanding. We can just do the derivative in one line, which is pretty remarkable. Let's go ahead and try one more. We have fx equal to 1 over root x, 5x to the e, and then sine of 3 pi by 4. So go ahead and pause the video and give this one a try. All right, so this we need to rewrite as x to the negative 1 half. And sine of 3 pi by 4, well, you might have thought about the unit circle and tried to figure that out, but let's actually see what happens when we do the derivative. The derivative of x to the minus half will be negative 1 half, x to the negative 3 halves. Here we're going to have negative 5 times e, x to the, well, e minus 1. And, well, the derivative of sine of 3 pi over 4, this is just a constant. And so it's very important that you recognize that this is a constant. There's no x involved. And the derivative of a constant is always 0. Watch out for those. You don't actually have to calculate the unit circle value. You can just write plus 0 and you're good to go. So for homework, you can try the derivative power rule worksheet. Now there's a few questions here with rules we haven't developed yet. We still don't know what the derivative of e to the x is. That'll be a rule for the next video. So you're going to have to wait on a few questions, specifically question 5, 6, 9, it looks like also question 14, question 15, question 16. These questions involve e to the x, and we haven't done the derivative of e to the x yet. So you're just going to have to wait on those ones, but we'll get to them shortly in the next video, and then you'll be able to come back and finish those ones as well. So hopefully you enjoyed this video, and as always, thanks for watching.